Union Public Service Commission, Assistant Professor in Military College of Telecommunication Engineering, 2022 Question Paper Solutions, Part 3, from question number 61 to question number 90. Question number 61. The energy gap for gallium arsenide is, correct answer is 1.41 electron volts. The energy gap or band gap is energy difference between the valency band and the conduction band in a semiconductor material. Energy gap Eg is equal to Ec minus Ev, where Ec is energy of lowest level in the conduction band, Ev is energy of highest level in the valency band. Silicon, germanium, gallium phosphide are indirect band gap semiconductor materials, whereas gallium arsenide, indium phosphide are direct bandgap semiconductor materials. Silicon carbide, gallium nitride are wide bandgap semiconductor materials having energy bandgap of 3.86 and 3.4 electron volts respectively. Question number 62. Maximum PIV value for germanium is closer to. Peak inverse voltage is the maximum reverse bias voltage that a diode can withstand without getting damaged or entering into breakdown. For germanium diode, approximate maximum peak inverse voltage is 400 volts. Correct answer is 1. Similarly for silicon, maximum peak inverse voltage is 1000 volts. Question number 63. Consider the following statements regarding clamper circuit. Statement 1. The network must have capacitor and diode, but it can also employ an independent DC supply to introduce additional shift. Statement 1 is incorrect. Clamper circuit is having capacitor and diode, but biased clamper only will contain independent DC supply. In case of unbiased clamper, there is no requirement of independent DC power supply. Statement 1 is incorrect. Statement 2. The magnitude of time constant must be large enough so that large enough to ensure that voltage across the capacitor does not discharge significantly during the interval the diode is non-conducting. Statement 2 is correct. For proper clamping action, time constant tau RC must be much greater than time period of input signal. This ensures the capacitor retains its charge when diode is off. If time constant is much greater than the time period of a signal, then charge is retained when diode is off for a longer time duration. Statement 3. Throughout the analysis, we assume that for all practical purposes, the capacitor will fully charge or discharge in 5 time constants. Statement 3 is correct. In RC circuits, after 5 time constants, capacitor is about 99% charged or discharged. Correct statements are 2 and 3, and correct answer is option C. Question number 64. If the Zener diode is employed as a reference voltage, it will provide a level for comparison against other. So it is voltages. A Zener diode operating in breakdown region maintains constant voltage, that is Zener voltage, across it. Because of this property, it is widely used as a reference voltage in voltage regulators, comparators, analog circuits, power supplies. This reference voltage is used to compare with other voltages in the circuit. Correct answer is option A. Question number 65. The saturation conditions are normally avoided because the base collector junction is no longer reverse biased. Statement D is correct. In amplification, emitter base junction is forward biased, collector base junction is reverse biased. Whereas in saturation condition, both emitter base junction and collector base junction are forward biased. Hence, saturation conditions are normally avoided because our collector base junction is no longer reverse biased, it is forward biased. Question number 66. The correct set of values of the silicon transistor parameters ICO, beta and VBE at temperature 100 degrees centigrade respectively are. Correct answer is C. 20 nanoamperes, 80 and 0.48. The reverse saturation current ICO is 20 nanoamperes at 100 degrees centigrade. Current gain beta is 80 and base emitter voltage is 0.48 volts at 100 degree centigrade. The reverse saturation current increases rapidly with temperature, that is approximately doubles for every 10 degree centigrade rise in temperature. The current gain beta increases with temperature. Base emitter voltage VBE decreases with temperature, that is about -2 millivolts per degree centigrade. Collector leakage current significantly increases with temperature, almost doubles for every 10 degree rise in temperature. Base emitter voltage VBE decreases with temperature, that is -2 millivolts per degree centigrade. The correct answer is C. Question number 67. Consider the following statements regarding network stability and sensitivity. Statement 1. Beta increases with increase in temperature. Statement 1 is correct. Statement 2. VBE decreases about 10 millivolts per degree Celsius increase in temperature. So it is not 10 millivolts, it is 2 millivolts per degree centigrade. Statement 2 is incorrect. Statement 3. Reverse saturation current doubles for every 10 degree centigrade increase in temperature. Statement 3 is correct. Correct statements are 1 and 3 and the correct answer is option B. Next question. Consider the following statements regarding N-channel JFET. Statement 1. The maximum current is defined as IDSS and occurs when VGS is equal to 0 and VDS greater than pinch of voltage. Statement 1 is correct. IDSS is the drain current with the gate short circuited to source, that is VGS is equal to 0. Once VDS exceeds the pinch of voltage magnitude, current saturates at IDSS. Statement 2. For gate to source voltage, VGS is less than, that is more negative than the pinch of voltage level. The drain current is 0 amperes. Statement 2 is correct. When VGS is more negative than pinch of voltage, channel is fully cut off. In that case, drain current is 0. Statement 3. For all levels of VGS between 0 and pinch off level, the drain current ID will range from IDSS and 0 amperes. Statement 3 is correct. We know from JFET transfer characteristic curve, ID is equal to IDSS 1 minus VGS by VP whole square. If VGS is 0, IDSS is ID drain current is IDSS saturation current. If VGS is equal to VP, then drain current ID is equal to 0. Statement 3 is correct. Here all the statements are correct and the correct answer is option D. Question number 69. Which one of the following provides a parameter specifying the maximum rate of change in output voltage when driven by a large step input signal? That is slew rate. Slew rate is the maximum rate at which output voltage of an op-amp can change per unit time. The units are volt per microsecond. It tells how fast op-amp can respond to changes in the input signal. Current gain is the ratio of output current to input current. Voltage gain is the ratio of output voltage to input voltage. And then CMRR, common mode rejection ratio, is a measure of how well an op-amp rejects common mode signals. Higher the CMRR, higher the common mode rejection ratio, better the op-amp is at amplifying only the difference between the inputs, ignoring the noise and interference common to both the inputs. Here the correct answer is C, slew rate. Question number 70. For an op-amp having a slew rate of 2 volt per microseconds, what is the maximum closed loop voltage gain that can be used when the input signal varies by 0.5 volts in 10 microseconds? Given slew rate is 2 volt per microsecond, change in input is 0.5 volts and change in time duration is 10 microseconds. Rate of change in input dVin by dt is 0.5 by 10 microseconds. that is 0.05 volt per microseconds. We know that the output rate of change dV naught by dt is equal to slew rate, which is voltage gain into input rate change, where AV is the closed loop voltage gain. So using this formula, voltage gain less than or equal to slew rate by input voltage. Given slew rate is 2 volt per microsecond, input slope is 0.05 volt per microseconds. So that is closed loop voltage gain should be less than or equal to 40. The maximum closed loop gain is 40 here. The correct answer is option C. Question number 71. The conductivity of copper at 25 degrees centigrade is, at 25 degrees centigrade, the electrical conductivity of pure copper is 5.96 into 10 power 7 Siemens per meter, making it one of the best conductors of electricity among the metals. The resistivity at 25 degrees centigrade is 1.68 into 10 power minus 8 ohm meter. Here the nearest answer for 5.96 into 10 power 7 is 58 mega Siemens per meter. Similarly, the electrical conductivity, resistivity, and thermal conductivity of different conducting materials are given in the tabular column. Question number 72. Consider the following statements regarding superconductors. Statement 1. Superconductors are materials with an electrical resistance that abruptly equals to 0 if the transition temperature drops below certain point. Statement 1 is correct. Superconductors exhibit zero electrical resistance below their critical or transition temperature. Statement 2. To achieve superconductivity, the material generally has to be cooled with liquid helium. Boiling temperature is minus 269 degree centigrade. Statement 2 is correct. For conventional superconductors, Tc is very low, around 4 Kelvin. They are cooled using liquid helium. Most early superconductors had critical temperatures well below the boiling point of liquid nitrogen, so liquid helium is required. Statement 2 is correct. Statement 3. Cooling with liquid nitrogen, boiling temperature minus 196 degree centigrade is only sufficient with high temperature superconductors. Statement 3 is also correct. High temperature superconductors have tran- transition temperatures above 77 Kelvin, that is minus 196 centigrade, so liquid nitrogen is sufficient. Conventional supercomputers Conventional superconductors require colder temperatures. Liquid helium for low temperature superconductors and liquid nitrogen for high temperature superconductors. Here all the statements are correct and the correct answer is option 3. Option D. Question number 73. Consider the following statements regarding winding connections. Statement 1. Star connections are cheaper for high voltage windings. Statement 1 is correct. In star connection, each phase winding sees only a fraction of line voltage. This allows insulation requirements to be lower, making it more economical for high voltage applications. Statement 1 is correct. In star connection, phase voltage is line voltage by root 3, Vp is equal to VL by root 3. Each phase handles lower voltage. Lower phase voltage means less insulation is required, that is cheaper for high voltage windings. Statement 2. Star connections are cheaper for high current, low voltage windings. Statement 2 is incorrect. For high current, low voltage windings, delta connections are generally preferred. Delta allows better current sharing and avoid neutral issues. Star connections would require thicker conductors to handle high current, making them less economical. In delta connection, phase current Ip is equal to line current by root 3. Each phase carries less current. Thinner conductors are required, which makes it cheaper for high current, low voltage applications. Statement 3. Delta connection in combination with a star winding reduces zero sequence impedance of the winding. Statement 3 is correct. In star delta transformer, the delta winding provides a path for zero sequence currents. This reduces zero sequence impedance and stabilizes the system using during unbalanced conditions. In star delta transformer, delta winding provides a path for zero sequence currents, that is circulating currents in delta loop. This reduces zero sequence impedance and stabilizes the system using during unbalanced conditions. Statement 3 is correct. Correct statements are 1 and 3 and correct answer is option B. Question number 74. Consider the following performance postulates regarding ideal transformer. So the characteristics of or assumptions of ideal transformer is no losses, that is no copper loss, no core losses, perfect magnetic coupling. The flux produced by the primary coil links with the secondary coil, that is zero leakage flux, zero magnetizing current, no current is needed to establish mutual flux in the core, infinite permeability of the core, and no saturation. Power balance, there is a power balance, that is input power is equal to output power because no losses exist in the ideal transformer. For the main assumptions of ideal transformer are zero winding resistance, no copper loss, no core losses, that is zero hysteresis loss and zero eddy current loss, infinite permeability of the core, that is zero magnetizing current, no leakage flux, 100% efficiency, input power is equal to output power, and voltage ratio is V1 by V2 is equal to N1 by N2, where V1, V2 are primary and secondary winding voltages. Current ratio is I1 by I2 is equal to N1 by N2, where N1, N2 are the turns in primary and secondary windings of the transformer. Let us see the statements. Statement 1. Low loss exist. Statement 1 is incorrect. Zero losses exist. Statement 2. Perfect magnetic coupling is displayed between the winding pairs. So coupling is perfect. Statement 2 is correct. Statement 3. Less current is required to establish magnetic flux. It is ideally zero current. So statement 3 is incorrect. In the question, which of the above performance postulates are not correct? So not correct statements are 1 and 3 and the correct answer is option B. Question number 75. A good transformer design should have two performance attributes, that is high efficiency and small percentage voltage drop from input to output. The typical values of these performance attributes in percentage are, so a well-designed transformer typically achieves 98% efficiency and voltage regulation 3%. 3% in practice. The correct answer is option D. 98% efficiency and 3% voltage regulation. Question number 76. Consider the following statements regarding ferromagnetic core material of transformer. Statement 1. Ferromagnetic core material of the transformer has two distinct mechanisms, hysteresis loss and eddy current losses. Statement 1 is correct. In transformers, core losses or iron losses mainly consist of hysteresis loss and eddy current losses. These occur in the magnetic core when alternating flux is present, and the causes for hysteresis loss is when the magnetic field in a core repeatedly reverse direction due to AC supply and the magnetic domains continuously realign. And the reduction techniques are use silicon steel cores, use materials with narrow hysteresis loop. Similarly, the causes for eddy current losses are alternating magnetic flux induces circulating currents inside the core material. These currents flow within the core material and produce heat losses. Reduction methods are use thin laminated cores and high resistivity materials. Hysteresis loss pH is equal to Kh into F B maximum power n into V, where Kh is hysteresis constant, F is frequency, B maximum is maximum flux density, V is volume of the core. Here hysteresis loss is due to magnetization reversal. Similarly, eddy current losses is equal to Ke B maximum square F square T square V, where T is thickness of lamination, F is frequency, B maximum is maximum flux density, and this eddy current losses is due to inducing circulating currents. Let us see here. The hysteresis loss pH is proportional to frequency B power n into V, directly proportional to the frequency. Statement 2. Hysteresis loss varies directly with frequency, while eddy current losses are dependent on frequency squared. Statement 2 is correct. Hysteresis loss pH is directly proportional to F, B, and V, directly proportional to the frequency. Eddy current losses are proportional to square of frequency. Statement 2 is correct. Statement 3. Both losses are almost directly proportional to flux density squared. So in case of history losses, N is 1.6 to 2. In case of eddy current losses, P is proportional to B square. Both losses are proportional to B square magnetic flux density. Statement 3 is correct. Here all the statements are correct and the correct answer is D. Question number 77. Voltage rating, current rating and maximum operating frequency for thyristors respectively are. The key ratings of thyristor are: voltage rating, thyristors can handle up to 10 kilovolts in industrial power applications, and current rating up to 5 kiloamperes, making them suitable for HVDC transmission, motor drives, and power control. Frequency rating, thyristors are not fast switching devices. The maximum operating frequency is limited to 1 kHz due to slow switching characteristics. The correct answer is B. Voltage rating is 10 kilovolts, current rating is 5 kiloamperes, and maximum operating frequency is 1 kilohertz. Question number 78. Which one of the following is not a left level triggered device? That is GTO, gate turn off thyristor, which is a pulse triggered device. Correct answer is C. And IGBT stands for insulated gate bipolar transistor, SIT static induction transistor, MCT mass controlled thyristors. These are level triggered devices. Question number 79. Consider the following disadvantages regarding power electronic converters. The disadvantages of power electronic converters are harmonic generation, low power factor, EMI problems, need for filters, complex control circuits, switching losses and heating, overload capacity of converters is low. Let us see the statements. Statement 1. The overload capacity of power converter is very high. Let us see the statements. Statement 1. The overload capacity of power converter is very high. So statement 1 is incorrect. The overload capacity of converter is low. Statement 2. The AC to DC and AC to AC converters operate at low power factor under certain conditions. Statement 2 is correct. Low power factor. Statement 3. It generates harmonics in supply system as well as in the load. So harmonics are generated. Statement 3 is correct. Correct statements are 2 and 3 and the correct answer is option C. Question number 80. The reverse recovery current of a power diode is 5 microseconds. Given reverse recovery time is 5 microseconds. The rate of fall of current is about 20 ampere per microsecond. What are the storage charge and peak reverse current respectively? So given reverse recovery time is 5 microseconds, rate of fall of current di by dt is 20 ampere per microsecond. The peak reverse current IRMS is equal to PRR into di by dt. Reverse recovery time is 5 microseconds, di by dt is 20 ampere per microseconds. The correct answer is 100 amperes. And charge stored is area of triangle half IRMS into reverse recovery time, that is half IRMS is 100 ampere, reverse recovery time given is 5 microseconds. Correct answer is 250 microcoulombs. The charge is 250 microcoulombs. Here option C is correct. Storage charge is 250 microcoulombs and peak reverse recovery current 100 amperes. Question number 81. Consider the following constraints regarding carbonated beverage containers. Let us see some theory related to carbonated beverage containers. The materials used for carbonated beverage containers must satisfy several important constraints because the drinks contain dissolved carbon dioxide and are stored under pressure. First one is gas barrier property. The material must prevent escape of carbon dioxide. Mechanical strength. Containers must withstand internal pressure created by dissolved oxygen during bursting and deforming. Chemical inertness. The material should not react with the beverage and should not contaminate the drink. Non-toxicity. Food safety. Material should be safe for food contact and should not release harmful substances into the beverage. Lightweight, cost effective, transparency, and this is an optional but desirable, good formability and recyclability. Let us see the statements. Statement 1, they provide a barrier to the passage of carbon dioxide which is under pressure in the container. Statement 1 is correct. They are non toxic, unreactive with beverage and are preferably recyclable. Statement 2 correct. Statement 3, they are relatively strong and capable of surviving a drop from a height of several feet when containing the beverage. Statement 3 is correct. Which of the above constraints must satisfy the material used in carbonated beverage containers? All the three above statements. Correct answer is D. Question number 82. Which one of the following is the sum of sphere volumes of all atoms within a unit cell? Correct answer is APF, atomic packing factor. Atomic packing factor is the ratio of volume of atoms in a unit cell to total volume of unit cell. It indicates how efficiently atoms are packed in a crystal structure. Atomic packing factor measures space occupied by the atoms in unit cell. Let us see definition of coordination number. Coordination number is the number of nearest atoms directly surrounding a given atom in the crystal structure. It describes how atoms are bonded and arranged around each other. The atomic pack APF atomic packing factor is volume of atoms in unit cell to total volume in the unit cell. It indicates how efficiently atoms are packed in crystal structure. For BCC, atomic packing factor is 0.68. For FCC, face-centered cubic structure, it is 0.74. In FCC, A is equal to 2 root 2 R, where A is unit cell edge length, R is atomic radius. In case of BCC, unit cell edge length is 4R by root 3. Your correct answer is C. Question number 83. For metals, each atom has same number of nearest neighbor or touching atoms is called. It is coordination number. So coordination number is the number of nearest neighbor atoms surrounding a given atom in crystal structure. Let us see the definition of other options. Atomic number is the number of protons in the nucleus of an atom. It uniquely identifies an element in a periodic table. Atomic density, the number of atoms per unit volume. Atomic density is number of atoms in unit cell to volume of unit cell. Next, atomic packing factor or package density or packing density, a fraction of unit cell volume that is actually occupied by the atoms, assuming a hot sphere model. Here the correct answer is A. Coordination number, the number of nearest neighbor atoms surrounding a given atom in a crystal structure. For simple cubic structure, atomic packing factor is 0.52. For BCC 0.68, for FCC 0.74, for HCP 0.74. Similarly, atoms per unit cell is in case of simple cubic 1, in case of BCC 2, in case of FCC 4, in case of HCP it is 4. Coordination number of simple cubic is 6, BCC coordination number 8, FCC coordination number 12, and HCP hexagonal close packed structure coordination number is 12. Here the correct answer is A. Question number 84. For body centered cubic crystal structures, the unit cell length is A, atomic radius is R. These are related as. In case of FCC, A is equal to unit cell edge length, A is 2 root 2 R. In case of BCC, body centered cubic, A is equal to 4R by root 3. The correct answer is option A. Question number 85. The coordination number and atomic packing factor of for HCP crystal structure respectively are. So for HCP crystal structure, coordination number is 12 and atomic packing factor is 0.74. Examples of HCP structure are magnesium, zinc, and symmetry is hexagonal symmetry. Here the correct answer is option C. Question number 86. If Na is Avogadro number, Vc is volume of unit cell, A is atomic weight, small n is number of atoms associated with each unit cell, then theoretical density rho of a metal is defined as. Here mass of unit cell is small n A by capital Na and density of unit cell is mass by volume, that is density of unit cell is small n A by Vc by Na. Correct answer is A. Question number 87. The modulus of elasticity value for iron at 100 type crystallographic orientation is. Iron is an anisotropic in its elastic properties, meaning the modulus depends on crystallographic direction. The modulus of elasticity depends on crystallographic direction. In case of BCC iron, 100 orientation 125 gigapascal, for 110 orientation 210 gigapascal, for 111 crystallographic direction 273 gigapascal. This directional dependence comes from crystal symmetry and bonding forces in different orientations. In case of 100 type crystallographic orientation, the modulus of elasticity is 125 gigapascals. Correct answer is option C. Question number 88. For materials, the magnitude of thermal stress sigma developed by a temperature change delta T dependent on coefficient of thermal expansion alpha L and the modulus of elasticity E are related as. Thermal strain epsilon is alpha L delta T. In stress strain relation, sigma is equal to epsilon E, where capital E is modulus of elasticity by using Hooke's law. Therefore, thermal stress sigma is equal to alpha L into delta T into modulus of elasticity. Correct answer is option A. Question number 89. What is the time to rupture for a component that is subjected to a stress of 140 megapascal at 800 degrees centigrade? Take the value of Larson-Miller parameter, Lm parameter as 24,000 and constant C is 20. Lm parameter is a creep life prediction tool. Higher temperature or higher stress, shorter the rupture time. So this LMP is equal to T into C plus log 10 TR, where capital T is absolute temperature in Kelvin, small tr is time to rupture in hours, C is a constant, where LMP is Larson-Miller parameter. Given LMP is 140 megapascals, temperature T is 800 degrees centigrade, that is 800 plus 273 1073 Kelvin, and constant C is 20. Substitute all the values in this LMP parameter, and on calculation we will get TR is rupture time is 232.91 hours. So that is 232.9 is approximately 233 hours. Question number 90. Consider the following statements regarding magnetic properties of materials. Diamagnetism. Statement 1. Diamagnetism is very weak form of magnetism and persists only while an external magnetic field is being applied. Statement 1 is correct. Diamagnetism is induced only in the presence of an external magnetic field and disappears once field is removed. Statement 2. Diamagnetism is induced by a change in orbital motion of electrons due to an applied magnetic field. Statement 2 is correct. The applied field slightly alters electron orbital motion, producing weak opposite magnetic moment. Statement 3. The induced magnetic moment is in the direction of applied field. Statement 3 is incorrect. It is not in the direction of applied field. In case of diamagnetic materials, it is in opposite direction. In, in diamagnetic materials, the induced magnetic moment is in opposite to the applied field. That's why diamagnetic materials are repelled by the magnets. The correct statements are 1 and 2, and the correct answer is option A. Let us see the properties of diamagnetic materials. Diamagnetic materials are characterized by their weak negative response to external magnetic fields, meaning they are repelled rather than attracted. The properties of diamagnetic materials are weak magnetism opposes external field, and it is a temporary effect. That means diamagnetism exists only while external magnetic field is applied. It vanishes once the field is removed. Electron orbital origin, temperature independence, magnetic susceptibility, which is small and negative. Permeability is slightly less than 1, meaning they reduce the magnetic field inside the materials.